Hello everyone, welcome to this video entitled Understanding Zero Voltage Switching in Half Bridge Converters, Part 2. So this is the second part of this previous video, Power Electronics number 79. So if you haven't watched this video, it's very advisable for you to take a look at it before continuing with this presentation. So in this previous video, we saw the introduction, we talked about the turn-off process of the half-bridge transistors, and today we will continue studying more things related to this topic. We will see the turn-on process in the half-bridge transistors and also the turn-on and turn-off process in the half-bridge diodes. Then we will see some incorrect designs and of course some Qspice simulations to illustrate the different ideas. Another relevant video that you may be interested in is this one, Power Electronics number 1, related to MOSFET hard switching process. So in the previous video we talked about the different switching patterns that we can have in the half-bridge converter, zero voltage switching, in phase or zero current switching, and we are in these videos focusing on zero voltage switching. Then we did a basic analysis of what happens in the switches and diodes during turn on and turn off. Later, we focused on the process of turning off, considering the parasitic capacitances that we have in parallel with the switches. These capacitances can be the intrinsic capacitance of the switches or even an external capacitance that we are placing to decrease the losses during the commutation. We did a detailed analysis during the switch turning off, and here we calculated the losses that we will have during the turn off process, and we also obtained the value of the capacitor that we need to have very low losses during the turn off process. And finally, we did a simulation in which we are showing the different waveforms to demonstrate how we can make the increase of the voltage across the switch slow enough. So during the turning off process, during the process in which the current through the channel is decreasing, we are going to have in parallel very low voltage and therefore the losses are going to be also very small. So let's see now what happens during the transistor turn on and diode turn off process. So this is here around this point when the current is crossing zero value. Here on the right we have a detail of what is happening. This is the zero crossing of the current. Here we have the gate voltage. So we have a dead time interval here, T sub D, and then we are activating the gate of the transistor. So before the transistor is activated during the dead time interval, the current, which is negative, can only circulate through diode D1 in parallel with switch S1, is the body diode of the MOSFET. But then at this instant TD, the switch is turned on. We are applying the gate voltage to the switch. So the equivalent circuit is as shown here. At the beginning we have the diode conducting the current level that we have at this point, I sub A, which is circulating through the diode, but then we are turning on the switch. So we can see the switch as a variable resistance at the beginning before applying the gate voltage. This resistance is very high, and when we start applying the gate voltage, the resistance is going to decrease until the on value. So because the voltage across this resistance is going to be very small, smaller than the threshold voltage of the diode, the current I sub A is going to circulate through the channel in this direction. So the transistor is operating as a synchronous rectifier. We have seen this in this video, Power Electronics number 14. So if you are interested, you can get more information about this by watching this video. So this is the idea when using a MOSFET as switch. Not only all the negative current is circulating through the diode. When we are activating the switch, this part of the current is going through the channel of the MOSFET. So this is a very smooth transition. It happens at very low voltage across the switch, so the losses are going to be negligible. At the end, the current goes through zero and then is reversed and going into the channel, also goes through the channel, but in the other direction. So we have a situation like this. The current is circulating through the channel in this direction, then the current reverses and go through the channel in the other direction. We can also see this on the characteristics of the MOSFET. This is the current through the channel versus the voltage across the transistor. When we are applying the gate voltage, we are on a characteristic like this one. And then if the current is negative, we are at a given point like this one. The current is going decreasing up to zero and then going up to a maximum value, which is around here. And all along this interval, the transistor is conducting through the channel. So there is a switching process here, but it is very smooth. It is not worth to study what is happening here because we are going to have negligible switching losses and we only have the conduction losses in the diode and also in the MOSFET channel. So here we have a simulation to see what we have just seen in previous slide. We are measuring the voltage across the switch, the current going into the switch, and also the gate voltage. So here we have the gate voltage. This is the dead time. And here we have the voltage across the switch and the current circulating through the switch. So in this interval here, before applying the gate voltage, here the gate voltage is 0. So in this part, this current is circulating through the body diode of the transistor. And this is proven because if we measure here the voltage across the switch, we get a value of minus 0.7 volts, which is the typical voltage of a diode when it is conducting. But then at this point here, the switch is turned on. So we can see that the voltage here is changing. And at this point, for example, for this value of the current, we have only a voltage of minus 2 millivolts. And this is so because now the current is going through the channel of the MOSFET. The resistance is very small. This is a very good transistor. The own resistance is only of a few milliohms. So the voltage is only minus 2 millivolts. And here at this point, the current reverses and goes positive. So at this point, which is more or less with the same absolute value of the current like this, we have a positive value of 2 millivolts. We can see also here some spikes on the voltage and also on the current circulating through the capacitor C1, the external capacitor, but as we can see, this is extremely short interval and the losses, as we are going to see later, are totally negligible. And the last switching process that we have is the turning on of the diodes, and this occurs at this point here and at this point here. For example, at this point we have transistor S1 conducting through the channel, then the transistor is turned off and the current goes through diode D2. So the situation is as shown here in these schematics. Transistor S1 is conducting the current through the channel, then the transistor is turned off, So the current through the channel is decreasing. Also the capacitances C1 and C2 are charging and discharging, as we have seen before. And once the voltage across capacitor C2 reaches 0, the diode D2 can start conducting the current I. Here we have the waveforms in time with the polarities that we are showing here, the current in this direction and the voltage with this polarity. So at the beginning we are at this point and the diode is not conducting, the current is 0 and the voltage is minus VCC. So on the characteristics we are at a point as this one here. Then when the charging and discharging of the capacitances occurs, the voltage is decreasing, reaches 0, and then it starts conducting very quickly. So this corresponds to this interval here. And we know that diodes are very good starting conduction, so we are going to have negligible switching losses. Let's do now an analysis of the losses by simulation, and for this we are going to measure the instantaneous power here in device M1, including the external capacitor. So we are measuring the voltage Vs1 and the current entering here, and same thing for transistor M2. So during the turn off of transistor M1, we have these waveforms. This area here is the energy which is positive, so this means that is energy entering here into this part of the circuit, while here we have a negative energy. So this means that this is energy that is coming out of this part of the circuit here. So finally, the total losses that we have during the off transition of transistor M1 is the addition of both of them, and this gives 0.64 microjoules. So the operating frequency is 100 kHz, so this means that this is like 64 milliwatts during this transition each time this transition takes place. And here we have the same energies during the on transition of transistor M1. So here is the gate signal of transistor M1. We have to remember that now the current is going in this direction, circulating through the body diode of transistor M1. And then when the voltage, the gate voltage of transistor M1 reaches around 4 volts, the channel is formed and starts conducting the current of the diode. The current, instead of going through the diode, goes through the channel of transistor M1, as we have seen. So as we can see, there is a small transient, but is extremely short, and the energies are very small, so we can consider that the losses during this transient are almost zero. Let's see now what happens with an incorrect design for which we have selected a too small dead time. For example, here this parameter tau, the time constant of this integrated circuit, is 50 nanoseconds, so the dead time is very small. So we can see here, this is the gate voltage of transistor M1 and this one is the gate voltage of transistor M2. So we can see that both transistors are conducting together during a given time interval, because we can see there are large Miller plateaus in both transistors during the switching process. So here in these waveforms we are showing the current that we have entering here the drain of transistor M1, and we can see how the current can reach a peak of 50 amperes. So this is a shoot-through current circulating through both transistors, which is going to create a lot of losses during the commutation. Here is the calculation of the losses in this case when we are using a too small dead time. The first thing that we can see is that both energies in both switches, including capacitance here and here, they are positive. So this means that both of the devices are absorbing energy. And if we calculate these two energies, we get a total of 2.75 times 10 to minus 5 joules. So for a switching frequency of 100 kHz, this means 2.75 watts. And we have to multiply this by 2 because we have this process twice per switching period. So this is a huge amount of losses due to the incorrect selection of the dead time. And here we have another example of an incorrect design in which we are using a too small external capacitance CS. In this case we have selected here CS equal to 1 picofarads, so it's almost like having no external capacitance in parallel with the switch. And then we can see here how the current which is entering in the switch, the drain current, which includes the channel current and the current through the parasitic capacitance of the switch, CDS, is decreasing in this way, and the voltage across the switch is increasing like this. So we have an interval in which we have a high current and high voltage together, so the losses are going to be higher. We can see here a comparison between both cases. In the case that we have seen before with 0.5 nanofarads, the current is decreasing quickly, and then we have an interval of linear charging of the capacitances in parallel with the switch. But here we have a superposition of voltage of current, and this can also be identified from the gate voltage of the transistor. So here we can see a large Miller plateau, while in this case the Miller plateau is much smaller. So this means that during this interval we are not following the ideal trajectory at constant low voltage, but we are following a trajectory like this, entering the active region of the transistor and therefore increasing the losses. And this is the calculation of the losses in this case with a too small external capacitance. So this is the energy E sub 1 of this part of the circuit, and this is E sub 2 corresponding to this part of the circuit. So we can see that this energy is positive. So this is energy that is coming into the structure of the transistor. Not all of this energy is dissipated in the transistor because we have to remember that there is a capacitance in parallel with the channel, so there is some reactive energy also. And this is the energy corresponding to this part, to the transistor, because now this capacitance is very small. So this is the energy corresponding to the transistor M2, and this is a negative energy because it's energy that is handled by the parasitic capacitance of the transistor. So the difference or the addition of both energies, considering the sign, is the total energy that is going to be dissipated during the commutation. And in this case we get this value 1.256 microjoules, which is almost double the value that we get when we are using an external capacitance of 0.5 nanofarads. So the losses are not very high because it's like this, 126 milliwatts at 100 kilohertz, but they are double of the losses that we get with an external capacitance. As a final comment, one interesting thing that I discovered while making this video is that using Qspice you can directly measure the current through the body diode of the transistor. For example, here we have transistor M1. These are the waveforms. This is the gate signal in green corresponding to transistor M1. The voltage here in blue and the current through the drain in green. And then we can measure the current going through the body diode by adding a plot and selecting here ID1 of M1. This corresponds to the current going through the body diode of M1. So we can see, as we have talked before, how the current corresponds to this interval in which the transistor M1 is still not activated. So the current in this small interval goes through the body diode. This corresponds to this part here. And then when the switch is turned off, the rest of the negative current goes through the channel of the transistor. And here even we can do a zoom and see that there is a small turn off transition in the diode corresponding to the reverse recovery of the diode, and this is the cause of the spikes that we can see in the current through the switch due to this transition that we have during this recovery of the diode. It would be very interesting if we could also plot the current through the channel of transistors directly to understand better the switching process, but this is not possible to do it directly. Even if we do the difference between the current through the diode and the current going into the drain, we won't get the current through the channel because we have the parasitic capacitance of the transistor in parallel. So maybe this could be an interesting feature for Qspice in the future. Okay, with this we get to the end of this presentation. I hope that you find interesting this information. Please let me know if you have any comment or question. Thank you very much for watching and I hope to see you in the next video. Goodbye now.